Yo, what's up, Internet? This is Synth Media here, and welcome back. We're on our third Protoplug tutorial. So Protoplug is a pretty cool VST plugin that somebody has put the Lua virtual machine inside. Lua is a programming language, and so by having the full power of a programming language inside your VST, you can code VSTs to do whatever you like. So you get Protoplug here from this site, Ozar, I think you pronounce it .fr. I'll put a link in the description. And when you open it up in your DAW, I'm using FL Studio here, you will get a kind of page like this where you can write some code. So I've started with one of the really simple examples they have given us to make a kind of sine wave based instrument, and I'm just going to adapt it today into a square wave instrument. The last video I did was just processing MIDI data. Today we're going to go back to process audio data. And I've been watching a few kind of YouTube videos of people building very basic kind of noisy square wave circuits, and I thought it'd be nice to have something similar inside our DAW. So the code starts off obviously requiring the library include Protoplug, and Protoplug brings in the whole framework of a VST plugin, and we start off with a couple of variables: frequency, amplitude, and pulse width, and I'm just setting some default values. Then those are kind of three parameters we're going to control in this synthesizer. The second part, a couple of variables here, are called the delta and the phase, and these are fairly typical things you use when you're going to generate a wave do some audio processing in code. So I just found a very simple example here. So a sine wave, let's just talk about what a sine wave is. A sine wave is based on the sine function, and the sine is a function of an angle typically. If you look at this YouTube video I've just put up here, I'll link this in the description as well, not mine, I'm just taking advantage of it being available. This line here, this kind of angled line, is at an angle to the horizontal, and the sine is a function of that angle there, and it produces just the vertical position. So as you increase the angle, you kind of go around the circle, you'll see we're going up round anti-clockwise here, and as we go up and down, this, which is just the graph of the height, goes up and down. So this is what a sine wave is. It's a function of this angle going round and round, and you can see it goes, you can keep going round as many times as you like, and you just keep on generating the same shape of wave. So that's a very typical mathematical function people are going to use in sound synthesis. And so we get in, the angle is very typically called the phase, and so basically this variable phase is just holding where this line going around, or where in going along here horizontally, where in the wave are we. The delta is going to be how much we increment our angle every time step, and the faster we increment our delta, the shorter the wavelength is going to be, the faster we're going to go around the circle, so that we're going to produce waves that are shorter wavelength, in other words higher frequency, and so the pitch will go up. Now the main part of Protoplug, or a VST plugin, is a function called process block, and process block is something that the DAW calls, so that typically a plugin doesn't generate an audio every sample point. Typically what happens is at a particular frequency, the DAW calls your plugin and says, hey, here is another buffer of audio data that I need you to fill. So depending on, in the options of your DAW, what you've set your audio settings at, like here we've got a buffer length of 512, every 512 sample points, what happens is that FL Studio calls into the VST and says, here's another block of 512 audio data points, sample points, fill that, and I'm going to blast those out of the audio interface now. And so that's what happens. And it calls your plugin by calling your plugin's process block function here. Now, plugin is something that comes by default inside the Protoplug thing. So here in Lua, we're just saying here's the function process block that's going to belong to the plugin object. The plugin object represents the whole VST world we're living in. And we get these two arguments from the DAW. This argument called samples is the array of samples. In our case, we know it's 512 points. And then this Smax is the actual number of points in that. So we know that it's the length of this buffer. Samples is the buffer, Smax is the length of that buffer. So here's how you do a loop in Lua. This is for I equals 0 to Smax. Okay, that's pretty... You may not have seen Lua before, but it's not very different from Python and JavaScript, etc. It's slightly different syntax, few gotchas, but on the whole, same sort of principles. So this is the bit of code we write to generate the audio. Now, what we do first is we generate this local variable s. So there's a local variable s, and we call that math sine function. If you remember, we were looking at the sine function here. Takes in the angle or takes in the phase as an argument and gives out the vertical position, the point of the sine wave. Okay, so we just take that. We've also got the amplitude, which obviously is the volume. So if the amplitude is 0, we're not going to get anything out, and the higher the amplitude, the bigger the amplitude of that wave is, the volume of the thing. So this S is just for every step through this loop, which is representing 1 point of the audio buffer to fill, S is going to have the position of a sine wave. But we're not making a sine wave. We're making, in our thing, we're going to make a square wave. So what I want to do is I want to say there's a threshold somewhere, and when we're above that threshold, instead of just playing the value of S, just play 1, which is like the maximum value of a square wave, and when we're below it, just play -1, which is the minimum value. The waves go between -1 and 1 in this data. So that's what this if thing here says. If the S is great. Now I'm calling that threshold the pulse width. That's not quite what you would think of a width is, but you'll see how it works in a second. So if the value is above the pulse width, that threshold, the value V is, we're going to set V to being 1. If it's below it, we're going to set V to being -1. So that just gives us a square wave. Then we take the actual samples buffer, which is a stereo buffer. So it's got, it's a 2-dimensional array, which has got a 0 and a 1. You know, the 0 is the left, the 1 is the right. And then the I, which is the counter stepping through it. And we just put in that square multiplied by the amplitude. In fact, we multiplied by amplitude twice here. I hadn't noticed that before, but still. And then all we do is the phase is just the angle, remember? So we're just going to increment that by the delta. And the delta corresponds to the frequency of the pitch we want out. So let's see how that looks. Now, I've set up a very simple user interface here. It's got these 3 values, the amplitude, the frequency. I've got Wave Candy, which was, I'm just using stock, apart from Lua, of course, Protoplug. I'm just using the stock plugin, so I've just got this Wave Candy. It's the best oscilloscope I could find. We've got these controls here. I've got the result going into Wave Candy, so I'm just going to start turning the amplitude up. Now what you'll see, if you can hear that square wave, and you can see our square wave is being produced. Now ignore these kind of edges where of the wave. I think that's just the thing Wave Candy does. That's why I say it's not the most kind of scientifically accurate oscilloscope. But the bit in the middle is just the square wave as you would expect us to be generating it. And I've got it at a frequency where it's fairly easy to see, but as we change the frequency, remember this frequency is changing that delta. Basically the delta is getting longer to run through the wave faster. Now I'll just make this sort of slow it down a bit. Now the important thing here we will see now is this pulse width. And now listen to what's happening as I change the pulse width. This is a sound that should sound quite familiar to you, but just hear how changing the pulse width basically means making that the higher or the lower part one longer, one shorter. Just watch the wave, listen to the sound. As you can see, we make the trough part of the wave shorter and shorter, and so the duty cycle, I think it's the duty cycle, the part that's in the duty cycle, more and more, the higher and higher proportion of it is high. And if we go the other way, we have the opposite effect, although the sound is not so different. You know, the sound, the difference between being 50-50 and being a short pulse and a long trough, or a long pulse and a short trough, that's the big difference. The actual extremes kind of sound the same. So that's quite a nice sound. At least, you know, that's kind of gives you some harmonic interest. If as you change the pulse width, you get some kind of movement. And you know, you've probably heard that sound in various kinds of synthesizer before. So let's just make it really clear what's going on here. I'm going to take, remember we took an S which was a sine wave, we just used this to what's sometimes called clamping, to clamp, you know, higher parts of it to one. So just to make that really clear, let's replace this V here with an S. In other words, let's to the left channel of our output we'll actually send the sine wave, and on the right channel we'll continue sending our square wave. And on the scope here I will increase the separation so we can actually have two separate channels, and we will recompile this code, go to this, and now you see the top one is our sine wave and our bottom is the square wave that got generated. Now, as we move, as you can see, what's happening here is when the sine wave is below a certain value, we go into the trough, and when it's above a certain value, we're in a peak. And as I change the pulse width, we're simply moving that threshold at this point downwards. So anywhere above here is becoming a peak, and anywhere below it is a dip. I hope this wind is not being... Right, so I'll take that back down. That literally, this function here, plug-in process block, is a very, very simple way of generating that square wave. Very simple synthesis, nice and noisy, nice and kind of harmonically rich. Unlike a sine wave, square waves have a lot of harmonics, and so if you were to filter that or do other things to it, you'll get some extra richness to the sound. So all we really want to talk about now is how you actually control that frequency and these parameters in the Protoplug. So I've defined a function called frequency to delta. Remember, what really controls the the frequency is the phase. Let's go back to making them both V again. As we're moving the frequency up and down, we're actually just changing the value of the delta so that the phase is incrementing faster. We would like a way though to calculate the value of the delta based on the frequency we would like in hertz. And now remember that the samples we're being given is sample points within a buffer, and also the buffer size is determined by the door, but also the sample rate of the whole door. The door itself is running at a particular sample rate. So it's important when we update this delta that if we really want to have things at a known frequency in hertz, we've got to figure out the appropriate correspondence between delta and hertz are based on the sample rate that our door is doing. Now here, I just got this from another example. This is just the standard way to do it in Protoplug. The plugin object has this method called isSampleRateKnown. It just says yes if we know what the sample rate is in our VST, and we have a method called getSampleRate. So the SR, we're just setting the sample rate. We're basically getting it from the door. The door is telling us, the plugin asks it, and if we can't get it, we default to assuming it's 44,100, which is CD frequency and its typical frequency. Then we do this bit of magic calculation, which is 2 times math pi times frequency over the sample rate. That gives us the delta we want. So we got that function. The last bit is the user interface. We've got this standard page within Protoplug under params. This is just how you create a bunch of sliders to get data into your synth. And here's the code for that. The plugin again has a thing called manage params, and we're just going to pass it a list, or if you remember my other tutorial in Lua, these are called tables, which are a collection of parameters. And the parameter has got a name. Here it's got, now this is a definition of itself, a little map or table or dictionary, however you think of it, and we're just passing a list of those. Remember in Lua there's just tables, so maps, dictionaries, associative arrays and ordinary arrays are the same data structure. They're all defined with curly brackets, so that defines the outer list or vector, but it's still also an associative array. And these are 3 little associative arrays inside it. All right, name as amplitude for the first one, and then change is a callback function. So every time someone changes this callback function gets called with the new value. And here, of course, it's the amplitude. So we just want to set our global variable, or it's called local, but local here means the scope of this variable is visible everywhere inside the plugin, and it's quite important actually. I've seen people miss out the local, and then inside the parameters you couldn't see that variable, so it's an important thing to watch out for. If you want to update any variables inside these callback functions, make sure they're scoped as local here, because local means local to the plugin, as far as I can tell. That's how it seems to work. So yeah, amp equals a val here. When it comes to frequency, okay, I took this, the actual bar seems to be going between 0 and 1. All I've done is I've multiplied it by 3000, so we get hertz between 0 to 3000, and then I'm calling that frequency to delta function and putting that in the delta here. So that's how we've set up our amplitude slider, that's how we've set up our frequency slider. The final thing here is the pulse width. Now the pulse width is really just this threshold, and if you think about your wave going from -1 to 1, it's 2. I've set max equals 2. That just means that within the pulse width slider we go from 0 to 2 at our extremes, and on the change, I just set the pulse width to val -1. So the pulse width is going to get a value between -1 and 1. So it's literally the vertical position within that wave that's the threshold between high and low. That's it. I mean, that gives us now you can hear the sound at higher frequencies. Changing the pulse width gives you different. In some ways it's more impressive at lower frequencies. Notice at the end, when the pulse width gets very small, if your volume is low, the sound just disappears. At this amplitude, the sound disappears here. If we make the amplitude higher, so in some ways that amplitude needs to be high, and then you may just want to control it somewhere else over here. That's end of part 1. That is a simple square wave synth, nice and noisy, in Protoplug. First bit of interesting audio generation. And now we are going to go on to part 2. Time for a coffee break, isn't it? I've got some coffee here. I'm going to drink some. Excuse the slurping. Something which is pretty useful for Protoplug is to go to this documentation here, which is the API reference. So if you want to know where I'm learning about the object, like the plugin object and its various methods, like manage params or the process block method, etc., this is where you look it all up. osr.fr, Protoplug API, modules, plugin. I'll link this in the description as well. Right, welcome back. And this is the next part. So hopefully that first explanation of making a simple square wave oscillator was understandable. And now we're going to move on to add some, well, what we would like to do next is to have more than one oscillator. So I want to take that code and I want to package it into a reusable object. Now, Lua is a bit like JavaScript in the sense that they decided not to go with the kind of class route. I mean, JavaScript now has classes, but originally it didn't have classes. It was inspired by Self and some of these other, what they called prototype-based object-oriented languages. And that can be a little bit confusing. So I decided to treat initially what I'm doing in Lua as though I was doing kind of a simple thing in JavaScript a few years ago. This may not be the best way to do a reusable object in Lua, but it's the simplest way I could do it that didn't kind of introduce too many more unusual things or extra complexity. So I've just taken that existing code and I've now refactored it to be in an object-oriented form or with an object. So I moved that frequency to delta function up here. It's the same one that we had previously. Now, an object in Lua is really just a table. Again, everything in Lua is a table. And if you remember, arrays are tables, dictionaries, maps, associative arrays, whatever you call them, key value mappings, these are all the same data structure, and objects are just the same data structure as well, and you can just attach to these objects functions as well. Just like you can put a number or a string, you can also put a function. And it's going to work kind of a bit like Python, if you've seen Python, where when you're inside a function that belongs to an object and you want to refer to the object that you're part of, you use the keyword self. Like Python, the fact it's called self is a convention, I believe. It's not an actual keyword. You could call it anything you like, but self is easier to understand. You will see a little bit of complexity. But let's start off then by saying we want to make an oscillator. All the data about one of these square wave oscillators is going to be kept in a table. And that's what you see here. This one says O equals and this curly bracket. That's me setting up the object. Now, I want to make several of these objects. So I'm now going to just create a function called makeOs. And I'm going to pass it these three values: the initial frequency, the initial amplitude, the initial pulse wave. And that's just to give it some data. This isn't quite a constructor in the traditional object-oriented sense, but you can think of it like a constructor. It's the function that takes these initial parameters and is going to make the object for us. And the way we make the object is literally just saying O equals and then a dictionary of all these key value things, or a table with these things like the frequency, it gets the initial frequency, the amplitude gets the initial amplitude, etc. Delta, we don't quite do this yet. It gets some default values for these things. It also gets a couple of functions. So or methods, let's say. Now, one method is I'm calling next here. So if you notice, the phase is itself part of the object. So it's remembering where it is along that sine wave. The object is remembering that. So next is just the function or the method that calculates the next output value and also updates the value of phase, right? So it's basically saying, what's the next of these positions of our sine wave? Sorry, what's the next vertical value of our sine wave? Oh, and also update your own internal phase value. Sometimes we call these things a phasor, a thing that kind of iterates through or runs through a phase. I'm just calling it next. That's like an iterator in other programming languages. So what do? The same as we did in the previous code. We have a local variable called v. I'm just creating that to make sure it's in scope at the right time. Then we calculate the actual value of s. Same algorithm as we're using before, right? Calculate the value of the sine wave s. If s is greater than the threshold, the pulse width, then v becomes 1. Otherwise, it becomes -1. Then we update the phase value by the delta. Now notice that all these instance variables or properties of this object that we declared up here, frequency, amp, delta, phase, they're all part of this object now. And so when we called next, we passed it an argument called self. And if you notice, we are referring to these variables, these instance variables, as self.phase, self.pulse width, self.phase equals self.phase plus self.delta, return the value multiplied by self.amp, right? That's just how we are referring to the instance variables or the attributes of the object we're currently inside. If you've used Python before, it's exactly the same as Python at this point. Okay, syntax a bit different, but almost identical. And remember here, we've set up this function, but there's just one more of these things inside this key value mapping. So we just have a comma at the end here. Now we also need some functions, some methods to update these values. So there's a set frequency, gets a self, and it gets the new frequency value, self.frequency f. It's when we call this function, we actually update. We call that frequency to delta function here that does the calculation based on the sample rate. So that's where we've kind of encapsulated, or we've hidden that away inside the set frequency. So set frequency, set amp, set pulse width, just the standard interface or API for updating the values of this, and next pulls out the next value. That's all it is. Where we declare this object in this function, assign it to O. Final thing we do actually want to calculate the delta. We didn't put the delta at this point because we don't necessarily have it, but let's just set the frequency, which we know does calculate the delta here, to make sure that at the point of initialization, when we create the object initially, the value is correct, and then we just return the object. So now we just have this function makeos, and every time we call it, we get a whole new map and a whole new object. Now we can just do this. We can just say local OSC1 equals makeos 440, bang. That's set us up with a new oscillator. Great. Now, when we come to our process block code, we do the same loop that we did before, but now instead of doing all the logic here, we just have to say v equals OSC1 next. Now, this is the thing to watch out for. Lua has some complexity in how you call methods on objects. Now, the crucial thing is if you see this, OSC1 colon next, right? If you use most object-oriented languages, Java, Python, Ruby, whatever, you are used to seeing something like OSC1 dot next. In Lua, if you just say the dot, which you can say, then you will not get the self, in other words, the reference to the object given by default. So if I were to do this, right, that's a bug, and it's going to be a confusing bug to you because it's going to be calling this function without any argument here. So you need to use this other syntactic sugar that they created, which forces it to, now in Python, for example, by default you don't have to write self in the argument list. If I'm calling a method on an object in Python, I always get the self by default. In Lua, if I use dot, I don't get the self by default. If I use the colon, I do get the self by default. This is going to be probably the number one thing that catches you out in Lua if you are not, if you've come from any other object-oriented language, you come to Lua, you kind of say, I can figure that out, that's all right. And you will forget this, and you'll put a dot instead of a colon, and your program won't work, and you won't know why, and it will cause you a great deal of pain and suffering. I speak from bitter experience. So I'm going to say it again, I'm just going to emphasize again. Think of your objects like this, with the self, pretend it's Python, but every time you call a method on an object, use this colon. That will make your life easier. Here's an example again. O colon set freq. Every time I call methods inside, if I'm just referring to an instance variable, self dot, whatever, but if I want to actually call a method and I want to make sure the self got passed, use that colon notation. That will be the thing that causes you more pain and suffering in Lua than anything else, probably. Apart from that, it's obvious, right? We've created an object that knows how to just update its own, that knows how to calculate, give you the thing, update the phase, etc. It's all encapsulated in that next method. Here in our main loop, we just have to do it. Parameters are the same again, except all we're doing now is remember, we made sure that OSC1 is local here. That means it's in scope within these callbacks for the UI. So again, OSC1 set amp, in other words, calling these methods for updating from the sliders. Again, notice the colon here as opposed to a dot. Remember that. If you learn nothing else from this video, remember that if you're going to call methods on objects in Lua, use a colon. Apart from that, code is as similar to the previous one as I could make it. And yeah, sure. pulse width works. Same as before, code same as before, just refactored into this more object-oriented form. Now, why would we want to do that? Well, we want to do that because now every new oscillator is a single line of code, more or less. Well, making a new oscillator is a single line of code. And, you know, if you think about it, that's always the great thing about doing stuff in software, is that if you want more oscillators, if you want more of the other components, you know, you just have to make a few more variables. You don't have to, you know, buy a big extra chunk of electronics. What am I going to do with that now? I'm not going to save that. I'm going to go to something a bit more complicated I made. So, what do I have here? I have something where I have created two oscillators. Let's have a look at the code here. Same object, os1, os2, and a third oscillator. It's also a square wave. So this is what I was kind of interested in. I was like, what a square wave low frequency oscillators sound like? Because obviously often people do low frequency oscillators with sines or triangle waves, but having a square wave kind of just means that you're going to be on or off, literally, in some sense. But I decided I'm kind of interested in that effect that people were getting when they were kind of making stuff with simple square wave handling logic electronics. I mean, that's where this synthesizer is going. I've made an LFO that was also just another square wave. And now in my process block, I do a couple of slightly odd... Well, handling the LFO was a bit more complicated, but let's forget the LFO for a second. V1 equals OSC1 next, V2 equals OSC2 next. I take the two, I sum them together, and I create this VF. We'll explain that in a second. That's basically the final value of V, which goes into the samples. Here, in my parameter list, all I'm doing is, well, I've got two oscillators, so I've got to have the three sliders for each oscillator, OSC 1 amp, freq, and pulse width, OSC 2 amp, freq, and pulse width, and some LFOs we'll get to, controls we'll get to in a minute, compile that. So how does this look initially? Maybe I'll pull this volume up slightly. So that's pretty standard. First oscillator, standard pulse width control, frequency. Right, it's just what we already know. Let's pull that down. Let's pull up our second one. Now we've got to mix the two. So we can we can drone them together, and you'll see now here is a mix of those two waves. The pulse widths still have an effect. So that's kind of, you know, fine, right? I mean, that's what we'd expect. It's the same object we were using previously. We've just got two of them. We've just mixed them together. Now, what I did with the low frequency oscillator, slightly different. So I get the value of the low frequency oscillator. again. Now in this calculation here, I said, okay, I don't just want to multiply the values by... So I'm using the low frequency oscillator to do amplitude modulation here. In other words, I'm changing the volume of the final signal of the mix of those oscillator 1 and 2 by this square wave. So we've got a square wave basically switching the volume. Well, I didn't want to have it so that the louder the LFO was, the louder the overall signal came. So what I wanted really was the LFO volume, amplitude, to control how much the LFO was affecting the amplitude of the other two. So I created another variable here called LFO amp, and you'll see that down here the LFO amplitude control doesn't change the LFO's own internal amplitude, it changes this external amplitude. It's really kind of like the mix level, in fact, of the LFO effect on the rest of it. So here I basically say take V, which is our mix of oscillators, times it by the mix level by the amp of that, and then we add that to the same thing multiplied by 1 minus. So effectively our signal is being a blend of... Our final signal, VF, is a blend of the original signal as amplitude modulated by the LFO and not modulated, and the original signal unmodulated by the LFO, and the LFO amp is really the mix level between the two. So let's go back and hear again our oscillators, and I'm now going to start turning up the LFO. First the amplitude, in other words sort of mix level of it, and then the frequency of it. Let's turn these up now. Have a listen to this. So let's have the LFO frequency very low initially, and this is much lower frequency than the, obviously. So start turning that up and have a look and see if you can see what's happening over here as well. Right, you can see the LFO is kind of gating now that the LFO amplitude is up. In fact, the LFO amplitude, as you go over there, it kind of turns it almost has the opposite effect. Let's leave it in the middle for a second. Right, so let's now turn the LFO frequency up. And we can turn it up to almost audio. So you can hear we're getting almost like it's not a frequency modulation effect, obviously, it's an amplitude modulation effect, because it's the amplitude of the main wave that's being changed by the LFO. Now you can hear that the pulse width will have some effect of that. It's a subtle effect. if you take the LFO amplitude down, then obviously the overall effect is lower. You can hear now with LFO amplitude down, with LFO frequency down, of course, it doesn't have such a difference. So with LFO amplitude down, it doesn't make such a difference. Okay, so nevertheless, you can see we've now started to make quite an interestingly noisy, let's say, drone synthesizer here in still a fairly short Lua script, right? I mean, we're 130 lines with all the spaces. You know, we've got 3 oscillators. Adding more oscillators would be fairly straightforward. You know, this is currently just a drone. We've not got any envelope shaping or and there's lots more we can do this. And so in future videos, I'm going to go on and develop this a bit more and add a few more extra things. But you know, it's quite fun now to play with. So I'm just going to put some effects on it in my chain. Let's put a bit of reverb on. You'll see I've got a flanger, I've got reverb, I've got delay. Let's just hear what it sounds like when I start putting that stuff on. Let's make you loud. Make you loud. Yeah, put the reverb on, smooths it a bit, but doesn't lose the quality of the sounds, right? Flanger on. And let's put a bit of delay on. Perhaps not as much delay as that. I've got quite a high time on that delay. So yeah, I mean this is really where I've got to with this, and hopefully you can see the potential. You can see how it's fine to do audio frequency synthesis in Lua. I mean, you wouldn't build in Lua a super complex synthesizer plugin, right, with many voices, etc. This is going to be for building your equivalent to these kind of simpler, cruder monosynths. But I mean, okay, what I like about this is it's giving us a certain amount of noisiness and grit and things that have a bit of glitchiness or extra harmonics. And, when you start running that through effects or filtering it, you're going to get all sorts of nice things out of it. So that's where we are with this. That's today's tutorial, and I hope it was interesting and informative, and thank you again for watching. I will be back. There'll be more developments on this. There'll be more developments on many other things. Sonic Pi, Protoplug, Pure Data, more altered beats and other kind of inspirations, a lot more crazy noise, and maybe even some music theory. Yeah, the usual stuff. So, if you like this, you want to know more about this stuff, do subscribe. Thanks for watching again, and I'm out, but I will be back soon.